Oh shit. Hello, good morning, everyone.
Good morning.
Hello. Hi, Kia.
Morning.
Good morning, Randy. Hi, Mehmet. Good morning, you guys. It's fantastic as always. Hi, Neil. Good to see you guys. Hi, Owen, Saja, Robin, Isla, Luis. Good morning. Good morning, Noah, also. Let me do a quick rearrangement of my screens. Good morning, Brian and Luis and Nathan and Andrea. Good morning. Also, Jonathan, hello. So I'm sure we're gonna get many more of you coming into class, um, just because it's 10 o'clock on the dot. So I'm sure more will come in and trickle in, and we'll get started pretty much then, or in like a minute or two. Um, Before we kind of continue on with chapter 2 and chapter 3, I did want to make an announcement for any of those who are new. I know we have maybe a handful of people who are joining us today for the first time. And everything that you probably have questions about is available on Canvas. And the best place to start is by watching the recordings of the first 2 days, because there is at least 5 hours of information available for you there, that we covered in class. So the good thing about Zoom is that you can do this on your own time and whatever works for you. And then if you still have questions, let me know and we can talk about anything after class today, when I have, you know, the time to give to you. Um, how are we doing? It's Wednesday, second to last day, halfway through the week, finishing the first week of January. Yes, Owen says it's hump day. That's true. Yeah.
Do we have
Uh,
class on Friday?
what?
Do we have class on Friday or is tomorrow Friday?
Tomorrow is our Friday. Thursday is normally Friday Junior, but in this class, Thursday will be like our Friday. So no, we do not have class on Friday, which I'm happy about. It's kind of like our catch-up day, right? Even though we're not in class, I think many of you, like me, will spend the day probably catching up on things. Um, yeah, and that's what it's for. Let's see, I see Daniela says enjoying the coffee. Yes, that morning coffee. I went the tea route this morning, and I'm gonna yeah, I'm gonna kind of dilute that one tea bag for a while, and we'll see how that goes. Oh, I see some of you were able to get completely cleared and at the course. I'm so happy that happened, because it's a process, and right now with everything being remote, it's time consuming, and it could be a little bit annoying. So yeah, so I'm glad for those of you who are going through it. Keep going through it. Let me know how I can help. And if you decide to take Physics 102 in the spring, and you have a different math course than the 265 266 series, you're likely going to have to go through that again. Yeah. Let's see. Oh, Keon, I was up watching the Georgia Senate results come in. Me too. I kept refreshing CNN. I was trying not to be as attached as I was during the elections. So yeah, they're still coming in. It's good. This is truly when voting matters. um, Yeah. Oh, Destiny. The class is Monday through Wednesday. No, I'm sorry. We're joking around too much. The class is Monday through Thursday. Yes. Thank you, everyone, for responding to her. Owen said yes. It's okay. Yeah, our class is Monday through Thursday. Hopefully, Thursdays will be like a wind down, but we'll probably have to catch up a little bit some of those weeks. And for example, this might be one of those weeks. Let's see. Yeah, election period was rough, and I totally agree with you. It was also during exams, and yeah, um, I gotta say that those are it's happening. You want to pay attention, you want to be aware of what's happening, but you also want to remind yourself of other things you have going on that are really important to your day-to-day life, um, as is those elections. But you also want to make sure you know get your stuff done for class too. Same here. Other good news: the Lakers won yesterday, just barely. If anyone saw that game, Jesus, don't get overconfident. Anyone? Yes, Amir, go Lake Show. I agree. Let me see. I'm the last announcement I have before we're actually ready to start today. Um, I wanted to talk about some of the services at trade, but I don't think our guest is available yet. So, yeah, I don't see her quite yet, but she'll be in soon. So maybe we'll hop in. Yeah. So before I continue chapter two, and we only just scratched the surface of chapter two, so um, if you started the homework and I saw some of you completed it, that's great. Just make sure you're following and having an understanding of it, and are ready to study those problems after you've had lecture and read about it. Um, are there any comments, questions, concerns about logistics or anything?
I had kind of a question about the lab.
Oh yeah,
The
yeah,
first
yeah.
the first lab. It's the so you want us to like draw pictures of the items that we find. Uh,
Yeah.
I like, and then you don't want us to draw like a picture of the label or like for instance like the manual or whatever, right? We
Cor-
just list them, but you just want the picture of the item.
Correct. And the picture is so that, like, for example, I think Randy maybe used a fire hydrant. And so let's say you drew a fire hydrant and you said the mass was about, I actually don't know in kilograms, but let's say the mass is about at least 10-15 pounds, which is maybe like 30 or so kilograms, right? Then that picture and just that visual will help me like say, oh yeah, that's about that mass. Or I think Mehmet used his roommate for one, and I could see a picture of his roommate and see the length and his height, and associate the two. But yeah, not details where I need to see the label, although that is helpful if you're drawing it. No, I just need to be able to associate the measurement with the object. Yeah. That's a good question. Any others?
Yeah, so I have the time, the mass, and the length. But I also included a couple where they were like the volume. Like I did like a lotion and like a mouthwash. Would that be okay?
Yeah, that's totally okay. Just one of the asks is that it's in the SI unit. So just make sure you convert to the SI unit. But if you're using a volume and you have something in cubic meters, that's perfect. That's really great. So for any of you who want to go past, or explore more of the units, by all means do it. I'm happy to see it, and it's really cool to see all the different things you guys come up with. So go for it. Let's see. I don't see her. Maybe no. Okay, well, maybe during the break or so, I'll keep my phone on in case I get a message of any sort. Yeah, we'll see. She's usually not late, so okay. Well, I'm going to switch gears to um, chapter two and get us started. I think we should be able to finish chapter two today. And I reworked a little bit of chapter three, the vector section, tomorrow. So um, I think we'll finish and we'll have plenty of time for questions and reviewing. So um, yeah, don't y'all worry. Okay, I'm just gonna start us up and get us to where we were yesterday. Give me 1 second. I hope I'm not a slide behind. Okay, I lost my Zoom window. Oh, I see a question. I'll get right to it. Give me 1 second to start this. Actually, let me get to your question. Andrea, do we need to show you the units conversion? Um, um, let's see. You should always show your work. But if it's a very complicated unit and you just happen to like look it up online, I'm okay with that too. Because really, I want to see that you can use the description of the unit, and the conversion is being practiced in other assignments. So if you want to put the conversion in, that's great, and you should show your work. But if you don't, for example, I think Owen said he was using different units, and if you just happen to look that up or just look at the bottle, that's okay too. Okay. Randy, do you have any questions?
I kind of do. Like when I was reading through chapter 2, I noticed that
Huh?
like the notation is different in physics. The like the subs of the Vx, like things like that. And when I noticed like when they were showing the derivatives, I understand derivatives, but I like understand them in a different notation, I think.
Yeah,
Like
that
there's like I get the dx dt, but I prefer like I prefer the x prime. And
yeah,
like
and
it was
that
kind of hard to see. And then I noticed like some of the d's were squared, like they had d squared t over dx, or dx squared over t or something, and like that kind of threw me off a little bit.
okay, so those are things we'll go over today. And the yeah, and Henry put it out there. When you see a d squared, it means like a double prime.
Oh,
So,
okay. Double
mhm.
prime.
Yeah, and the reason I asked if Randy had a question is because on my screen your box keeps lighting up. So it's like
Oh,
it knows. It just goes that way every few seconds. But I know it's because you're unmuted. But um, yeah, so we'll go over that notation, and I notation is really important, and I'll say that you'll see the most differences in notation in the beginning of chapter 2, and as we go through chapter 3 and 4, you're going to start to see a switch in the notation. That's something that's more practical and something we're more comfortable with, and you'll see in your other classes too. But in the
like when
beginning,
I see a v sub x, like av, how would when I like, it's really important for me to know like how, when I'm reading that in text, like what does that say? Like
yeah.
is that like the average velocity of x, or like
Yeah,
could you say
yeah.
it?
So let me show that screen, and this is a perfect place to start. I'm actually going to start one slide back um, because of this question, and we did mention it yesterday, and it's very much worth repeating because this notation will come up, and this notation will really help you keep organized, and that's part of the the game of physics, is staying organized in your calculations. Okay, so I think you guys should be able to see my screen, and I'm gonna go one back, and then okay, so this is we finished on the slide you just saw, and now we're going I'm just going to go one backwards to start with the definition of average velocity. So what we saw when we were talking about motion is that we're always looking at how position changes over time. So for position to change over time, we have to measure those intervals, those increments. And so on any graph like this, you will see some change in time. And because this change in time is on the x-axis, we're really looking at how the graph, the curve, is changing along this x-axis. And that's our time unit, right? So final minus initial. And then we also look at how that position is changing. Um, so let me see, I can't see who that is. I actually forgot to change one of my screens, so let me move those around. Okay, so we also want to see how the position is changing, right? So that position happens to be plotted on our x-axis here. So then we're going to look at how that value along the y-axis is changing. So we can define our average velocity then as that change in x, the change in position over the change in time. And this is how we write that. The first thing you'll see is that you have this sub x. This sub x is to denote that we are working in one dimension only, and that we are working along the x dimension. Something that you might see in the book or in other problems is a sub y. That would then tell us that we're working in the vertical, as if an object were falling instead of an object, a car moving horizontally. And then the last thing you'll see on the subscript is a comma average. And this is very specific to denote that we are working with averages here. In physics and engineering and STEM language, we're going to usually work in very exact moments of time. And when we work in exact moments of time, we're using the instantaneous values, and those instantaneous values will just be written as is, as velocity. So when you see this velocity here, this means a velocity that's an instantaneous velocity, and that's an x, y, and z. When you see this here, this will tell us that we are working with velocity in the y direction, and because there's no average on here, it would be the instantaneous velocity. So notice that until we get into our common use of instantaneous velocity, we're going to have to always denote that we're using average. And Daniela has a question. Would it be correct to say v sub x is velocity in that one dimension? Yes, v sub x is velocity in that one dimension. The reason we write x is because we're working on the horizontal. Yeah, that's the only reason. So.
And like, how would it read? Like, say, as far as like so you're reading it in text, and it's like, I want to say like the velocity of this particle in the x direction, the average velocity of x of this particle in the x direction.
Yeah, so that's one way to say it, and there's several more. You could say that the car is moving on a straight line. You could say that this is moving on a horizontal plane. If it's moving on a straight line, you usually want to assume that it's horizontal, just because that's our everyday way of writing things, along the horizontal. Also, you're going to find out in next week in chapter 4 that when we work in the vertical, there's few more laws that we have to account for, gravity really. So it'll have different ways, and we do have to recognize the wording. So part of learning physics is really figuring out what is being said in the problem, and we're going to focus on that a lot next week. So yeah, you'll see something like a horizontal plane moving in one line, moving in one dimension. Sometimes it'll straight tell you it's moving in the x direction. Yeah, so we have to be able to translate those. Okay, so now that we have our average velocity, we want to actually calculate this, but we want to also note that, again, everything that we are describing physically can also be described mathematically, and we want to make those connections of what math tools do we have that can also help us describe what's physically happening. So what we saw in the last slide, that we looked at it, and we looked at the average velocity as being as a change in position here over a change in time, which in math is a change in the y-axis over a change in the x-axis. So this very much also relates to the slope, the slope of an equation, right? Because if we look at how this position changes and this horizontal position changes, you'll see that we make a right triangle, and this line will be that hypotenuse. This is going to get us very, very close to our calculus world and our tangent lines really soon. And you also want to recognize these triangles anytime you can, because we're going to use it a lot in chapter 3 for vectors. Okay, so the slope of this line ratio then is equal to our average velocity. So I think I wrote this yesterday, but I'm going to write it one more time here. Vx average. Vx average then is equal to delta x delta t, and you would also see this as the slope, right, which is equal to, I'll just write the rise over run. so that we don't confuse ourselves with the y's and the x's. So here's your math connection, right? This slope, the line of this, the slope of this line ratio is equivalent to the average velocity. So anytime you see a graph and you do not have the line of the equation of the line, you could use the slope to figure out this value. So if we wanted to, for example, get the average from points A to B, we would just need our x final minus x initial, right? And our change in time, t final minus t initial. Yes, and t final minus t initial. Okay, I just heard from our guest. Let me just tell her. Okay. Okay, so we have our values here, you know, and you could pretty much do this from just taking the final minus initial, or you could equate it to yourself as a slope, and just take the rise over the run and you'll get the same value. So let us try this now example in a problem. So here you're given a picture in the graph. That's always helpful. Find the displacement and the average velocity of the car in the figure between positions A and F. This is a problem that's very directly, like, the wording is straightforward. It's not like the textbook that kind of throws you for a loop sometimes. So what you really want to do here is right away identify what it is you're looking for, what it is you're trying to solve for. Find the displacement in x, we know is delta x. Find the average velocity, and notice that they say average velocity, so that is our Vx average, and we can assume that it's x just from, you know, the drawings that are here. Between positions A and positions F. Okay, so we can use any one of these to help us out, and we also know some values from the table that we could try to remember. So let's start with the displacement, xf. So here, final minus initial will be x, f, which is final, minus xa, which is the initial. And so you could write this in different ways. You could start with that notation and then change it to the notation that's in the book or in the problem. And either one is correct. As soon as you get comfortable, you can switch to your notation that is in the problem. I think it's worth writing out the full equation. Yeah, it helps. Okay, so here's our solution, and you see, you can see without a word problem what it is you're solving for by reading this equation, the displacement of x from the F position to the A position. You now then take your values, right? From the table, we knew that final was negative 53 meters, somewhere around here, right? Negative 53 meters minus the 30 meters from A. Be careful with your negatives here. Be very careful with your negatives. For example, if A was a negative, this would have been, I'm just going to write an example, negative 53 minus 30. If A were a negative, just an example. Be careful with this. This is just an example. Okay, so then here we could very nicely then get our displacement of x is negative 83 meters. And this makes sense to what we see in the drawing. We went backwards some distance. Okay, then they ask us for the average velocity, and we know that the average velocity includes the displacement. So here we can start, and we can solve this in a few ways. So there, if you start with your equation here, let me see, Vx average, right? Vx average would be the displacement x final minus x initial. In this case, xf minus xa, right? Over that change in time that then happens. Someone needs the previous slide really quickly. I'm gonna go back quickly, but when things, for some things like this, just, you know, let me know if you're good, and I'll go back again really quick. Okay. Okay, so here we want to calculate just based again on the values that we have with our equation. So you write out your average velocity equation, xf minus xa. This is just the displacement that we figured out on the other side, minus the change in time. And here, you know, we got minus 83 meters. You could even jump down to this place of the equation, minus 83 meters over 50 seconds, and we get negative 1.7 meters per second as the average velocity. Now let's see, does that kind of physically make sense, right? So if you're looking at this average velocity from one line here, A to B, the slope would look like that, from B to C, and then going from like C to D. And notice that the slope of the line eventually going from A to, oh my God, I totally missed F, but that's close enough to F. But the line is sloping downwards, right? So this negative here does make sense to us then. So we have negative 1.7 meters per second here. So this is the average, and the average is something we're going to use really only in this chapter and in the beginning of this chapter. And it's only to get us in that mindset of what is an average? What is an overall look? And then how do we relate that to a moment in time versus an hour of time, right? So this brings us to our instantaneous velocity. Okay, guys, put your calculus hats on. But again, just derivatives. That's all we need here. So we're going to work on trying to go from average velocity to instantaneous velocity. So many times you're going to want to know what is the velocity of anything at an instant in time. So at some moment where it's frozen in time. And here what we're doing is we're looking usually at some large moment in time. So from A to F, we're looking at 50 seconds. But what if we want to start more specifically figuring out what is happening in shorter intervals or at a specific moment? You would reduce that line, right? From A to F, let's say then we wanted to look at A to E, that's 40 seconds. We go from 50 to 40, or eventually, right, A to D. Notice how the line changes. Eventually from A to B, and that's our 10-second interval. But what if we wanted to go even less? What if instead of 10 seconds, we wanted to look at 9 seconds here, right? Or 7 seconds, or even 5 seconds. You notice that this line here is going to become more and more and more tangent to the specific point of time that we're looking at. And when you eventually look at one very small interval of time, let's say, you know, 0.1 of a second there, you'll see that this line becomes tangent to that point. And when we do that, we're limiting the time interval as close as we can to 0. So here, delta t was about 50 seconds, right? From A to F. From A to B, delta t was about 10 seconds. And finally, we get down to 9, 8. And so what we're doing is taking this time interval and reducing it as close as we can to 0. So you might get some flashbacks of what we're doing here. So our instantaneous value, yes, we're looking at limits. That's right, Jose. So the instantaneous value of Vx, V sub x, is that limiting value of this ratio delta x over delta t. We're starting to limit that time interval of this slope, of this line ratio that we were just looking at in the average. 50 seconds to 40, 30, all the way down until we get to as close as we can to 0. And that 0 represents the time, that time interval that we are interested in. Not necessarily the number 0. It just represents that the time interval has been cut in a very, very small number, as close to 0 as we can get. And so this is how you guys have seen limits. Then the instantaneous velocity is defined as that limiting value as delta t approaches 0 of that line ratio, right? Our average velocity, delta x over delta t. All of this is equal to, in your calculus notation, the first derivative of x, dx of dt. So this is how you see it. And I personally like to write it this way. I like to write d of dt of x. And the reason I do this is because we're gonna eventually in all your classes, not just physics, whenever you differentiate or take the derivative of something, integrate, right? You have a long formula sometimes, and you really want to make sure don't get those variables crossed in any way. So I like to take the derivative out, which reminds me I am differentiating with respect to t, and I am looking at how the position is changing. So I like to write it this way. Um, so we won't really be using the limit way of getting a derivative. We will go straight to derivatives. And if we do not have an equation to get a derivative, we can use the slope. You can always use the slope if you do not have the equation of the line. I hope that's okay. Let's try this question now to see if we got like a grasp on what it is we're looking at, like average versus instantaneous. Members of the highway patrol are more interested in what? Are they more interested in what is your average speed or your instantaneous speed as you're driving? And think about how they're measuring this.
Instantaneous speed.
Mm-hmm. I see a lot of you saying B's. I heard Randy say B too. Yeah, all of you are correct, because what they're doing is if they were just using their eyes, right? Their eyes would probably be like an average, right? Because you're just kind of looking at them and making a guess from here, from one point to another, how fast they're going. But they're using that gun, that sensor, and that literally is taking a snapshot at one moment in time of you passing this sensor. And so that is an instantaneous speed. And so all of you, Henry, Mehmet, Saja, Luis, and Jonathan, Robin, Jose, Brian, Noah, and Randy, yes, B should be the right answer. Let's see. Yes. Woo. So that's the huge difference, right, between an average and an instantaneous. But again, you can use both methods to find your answer. Let's go a little deeper. Take a deep breath. Let's try this problem. A particle is moving along the x-axis. Oh, this is nicely written. A particle moves along the x-axis. Its position varies with time according to the expression x equals negative 4t plus 2t squared, where x is in meters and t is in seconds. The position time graph for this motion is shown in the figure. Now, this is a clue sometimes to how you can do these problems. Because the position of the particle is given by a mathematical function, an equation, the motion of the particle is known at all times. We have an equation. Well, yeah, we're given an equation. So if you wanted to jump to calculus and use your derivatives, you could, but you don't have to. They're also giving us a whole bunch of slope lines, so we can use that too. Notice that the particle moves in the negative x direction for the first second of motion, is momentarily at rest at the moment t equals 1 second, and then moves in the positive x direction at times t is greater to 1 second. So this problem wrote everything out for us. And when you look at a graph, this is kind of the thought process you want to go through. You want to first identify, okay, position versus time graph. You see a graph, a red line. This is the red line is what the curve is in the graph. And they give you an equation that represents that red line. And then they describe it to you, right? Notice that in the beginning, the particle moves in the negative x direction for the first second of motion. Notice that this is the negative x position, but we might associate this word with the x-axis, and that might confuse us, but the negative x position, direction. So we go in the negative x for the first second, and then we stop momentarily at t equals 1 second, and then we start moving in the positive x direction. So this is a good way to just, when you see a graph, you should read the graph this way to follow what's happening in the graph. Okay, some things that they didn't mention. There's a position A, B, C, and D, and they give us some slopes also for, it looks like maybe position A, and the slope maybe from B to D perhaps, and then a green line that looks like a tangent line or a slope line also for position C at some time. Okay, let's see what the question is. Determine the displacement of the particle in the time intervals t equals 0 to t equals 1 second and t equals 1 second till t equals 3 seconds. So our displacement equation, this is where you want to start. If you have no idea where to start with the equation, x final minus x initial. Okay, and here our first set of data is here. T equals 0 to t equals 1 second, right? So here we're going to have to look at our graph and figure out what are these positions and put in the time intervals that we need here. And we need to do this for those positions t equals 1 to t equals 1 second. So final minus initial, or you can write it as a to b. See, this helps us stay organized, right? From A to B, final minus initial. So we need the position at B minus the position at A. So we take this equation and solve it for B, and we take this equation and solve it for A, right? Okay, so for at position B, we are at 1 second, right? Position B is at 1 second. It also tells you here that that's that second point. So you put 1 into your formula and you get an answer here. And then you do the same thing for position A. For position A, we're at 0 seconds. And so this very nicely comes out to 0. So whatever this is, -4, I'll have it -4 plus 2, because 1 squared is 1, which is -2 meters. So our displacement then from A to B is -2 meters. Now you guys practice, do the same for t equals 1 second to t equals 3 seconds. You can write it out. Instead of it being A to B, it's gonna be from B to D, right? So from the displacement from B to D is still final minus initial, where final is D and the initial is B. And now you take the entire formula for X, right? This is the entire formula for X, and plug in the time at position D, which is 3 seconds. And we do the same here too. We should probably,
Is it appropriate to like do like x of t, like with t in parentheses, so that we know, so it looks familiar, you know, like so we know where we're substituting in the t's?
You mean like writing X of T here?
Yeah.
X of T equals -4t, like that?
Yeah.
Yeah, you can do that. Yeah. It's not too common. I don't see it that much in this textbook, but you will see it and you should be able to at least recognize, you know, what it is you're writing. Okay, so our answer then here is plus 8 meters. All right. I'm gonna, you know, rely on you guys that this math is correct. I think it's correct. Okay, let's go to our part B of our question. Everyone hold on, hold tight, okay? Calculate the average velocity during these two time intervals. Average velocity is not the instantaneous velocity, so don't jump right to it. I know that's what we want to do, but yeah. Owen has a good question. Is it necessary to put the positive in front? Not really. It's not super important. You won't get like dinged for it. It is important to put the negative if it's negative, but not the positive. They probably just did it to make it more obvious that it's an increase in displacement, like a positive motion moving in the positive direction, probably to the right. Okay, so let's try an average velocity now between these two time intervals. So we get our average velocity equation first from A to B, and then we'll do B to D. And we have that displacement already that we calculated on the other side, -2 meters. And the time change here is only 1 second. So our average velocity is -2 meters per second. This one's pretty nice and straightforward, right? And then we do the same for B to D. We take our average velocity, the displacement from B to D over that time interval, 8 meters over 2 seconds. And here you get that plus 4 meters per second. And again, they're putting the plus in, not to emphasize that it's positive, but to emphasize that it's an increase in the average velocity. That's really what it's there for. Okay, I think these are okay. So we're gonna jump to it find the instantaneous velocity of the particle at t equals 2.5 seconds. So our instantaneous velocity then, let me find some space to write, maybe right here. Instantaneous velocity, now we can just write velocity is equal to dx dt for, I forgot this notation. I think it's somewhere down here you write it, right? T equals 2.5 seconds, something like that. So all of you have taken calculus, so I'll wait for an answer. And then we'll look.
I would do like x prime of 2.5.
Okay.
Like
Can you
in
rewrite
parentheses.
the equation, please?
What?
What was the equation again?
I don't know. Let me see. Let me see if I can find it. Negative 4t x equals negative 4t plus 2t squared. Yeah. Oh, okay. Oh, thank you, Owen. Owen had it in there too. Oh, and Henry also says draw a vertical line and then t equals. Oh, yeah. Thanks, Henry. I remember it after you said it. Oh, I remembered it because you said it. Yeah, that's true. That's the way. Now, guys, don't get too hung up on this. You know, as it's totally okay if you know it as x prime. Use x prime. Ultimately, x prime and dx dt mean the same thing.
What's the line thing though? Like, because if the book is going to represent it one way, I want to make sure I know that.
The book doesn't show it this way. This is a calculus way of writing it. So I think in calculus, it's just a line to separate what the time interval is.
Is that like what you do on an integral? Like you do like this to that or something?
I don't remember on an integral. On the integral, you do this, right? Like this.
So yeah, my teacher showed me that way, but then he showed me that the way you did it with that straight line because he said that it helps you not get confused with the brackets.
Oh yeah, that's totally true too. I think I learned the bracket, but I use the line, even in the integral. But again, totally, I don't know. I don't think I would look too much into it, but this, I actually don't think I ever see it in the book this way. But maybe it's there. I don't know. Yeah, Owen says you can do either. It's clarification for what value to evaluate at. Yes, that's what this line tells us. That's what this line tells us. Evaluate at this point. Okay, can I get an answer? Anyone out there? Okay, I got one answer. Can I get two more answers? In support or negating? Oh, okay. Owen comes with the solid. It's 6 for sure. Okay, so I hear 6 from a lot of you. Now, we'll double check this, and again, we can do this with our derivatives. Luis got 10 on Owen. Okay, so we can do this with our instantaneous velocity and our derivative values, but you can also use the slope of the line. You can also use the slope of the line. So we want the velocity at t equals 2.5 seconds, which is right here, and this is point C. So this is the tangent line at this point here, all the way down to this point here. Those are the two ends. So we could also do a rise over run here, and very nicely this ends at 10 meters and -4. So that's where you see final minus the initial. And notice, we're very careful with the negatives here. And then we look at the time, which is a little bit harder to see, but 3.8 seconds minus the 1.5 seconds, which is the initial. And we get plus 6 meters per second. This agrees with the derivative of doing this too. So you can use either way. You might want to say key on 10-4. Yeah. You might want to figure out which one is easier for you. If you're given the equation, probably the derivative might be easier for many of you. If you don't have the derivative and you're given a slope, you can use the slope. Yeah. Let's see.
You mean use the slope to find the derivative, or use the slope like of the tangent line?
The slope of the tangent line, which is mathematically equivalent to the derivative.
Okay.
And then Luis says, the book explains it using the endpoints of the tangent line, but the derivative feels a lot easier. Yeah, it really depends on what you're given and what you have. You're not always going to be given an equation of a line, an equation, so you might need the slope. And the endpoints of a line are usually easier because you can see those values easier. That's all it's for. So if the endpoint is on a 10 here, right, like that's really easy to read. What's might not be as easy to read is the downward, but here you really got to just kind of make a guess. Let's see. Yeah, I also am with you guys with the derivative, but again,
Is it
uh-huh.
so? Like I was taught that in physics, well, I was taught in physics that it's inappropriate to estimate. Like you can't really estimate other than like halfway between 2 points that you're given. Like the
Mhm.
precision or accuracy or something
Mhm.
of your estimation isn't correct anymore if there's no like markers or something like a measured. You know what I'm saying?
Yeah, but if you're given this graph on an exam and you're not given an equation of a line, you got to make a guess.
So like we're allowed to say 3.75 rather than
Yeah, and
what
I would note that,
73.
right?
Okay.
Yeah, like and that's a good question. If you're not given an equation of a line and you have to make a solid guess, you want to make that guess as best as you can. So I would, draw that straight line, and I personally would make those tick marks, like this is halfway, this is another halfway. And if you said 3.75 and took that calculation out, I could follow that and see that it would be correct, or it'd be close to an estimate, especially based on a graph. Yeah, so if you have to, you can make that. But what they mean by not making estimations is that we do normally use instantaneous values and we do normally use the derivative. um, yeah.
Like, it was like about measuring in chem, like measuring things. Like they
Mhm.
would say, you can't say that's 2.25. There is no 0.25 line. You can't
Yeah, and
say that.
and that's appropriate for what that measurement of what they're doing, but for this problem it's okay to estimate. So
Okay.
yeah, you really want to be able to figure out when is it right to be very accurate and when is it right to estimate based on what you're given. So here, yeah, an estimate of 3.75 I think is within reason, and I would, if I were grading that, it'd be right to me. Oh, and Owen says, where does the -4 come from? Never mind. Yeah, -4 comes from here. And this is that point of the line. Okay, so the big picture here is that what we're doing is looking at how position is changing over time. And we can make one last kind of comparison between an average velocity and an instantaneous velocity and get some equations out of this too. So let us say we're going to look at the simple case of when a velocity of a particle is constant. So the way that you're, let's say, driving down the freeway and you're on cruise control, right? So that means your velocity is constant the entire time. In that situation, anytime you look at your average velocity, it will equate to your instantaneous velocity because your average velocity is staying constant, right? I hope that makes sense. I'm going to draw a quick graph just to show you guys. So let's say you're on cruise control and your average velocity is about 80 miles per hour. Okay, 80 miles per hour. So this is what your line of the graph, your line of your average velocity would look like. So at any point, at any frozen moment in time, anywhere along this interval of time, every single instantaneous value will equal the average value because you're constant over time. So with that, we can create our first and derive our first kinematic equation. Okay. So we have these two definitions for velocity. We have the average velocity defined as a displacement over time. And now we can say that the average velocity, when it's constant, can also be used as the instantaneous velocity over time. And so we can make a change here, and we can also derive an equation. So let us use the definition of the displacement and rewrite it for now the instantaneous velocity. If you're writing this down, It's okay to write it down. I don't think you need to write down the derivation because it's here. You will not get tested on derivation. You just need to know the equation. I'm more concerned with you knowing where these equations come from. So follow the derivation. Okay, so using the definition of displacement, final minus initial, we are going to rewrite our definition for instantaneous velocity. So we use the definition of displacement and we're going to put it into that equation there. Notice that there's no average here, right? Now we have this equation here. So our next step then is that we want to, in most cases, figure out what is the final position of the object. And so we're going to rearrange this equation and solve for this final position, just with what you see here. And so that's the equation that you see now, right? The delta t comes over to the velocity, and that's here. We add the initial position back over to this side, and there it is, your first kinematic equation of the 5. Very easily derived from the assumption that the average velocity or the velocity is constant over time. This equation, you'll see, is always written with this constant velocity, just so that you kind of keep note that this equation is only used when velocity is constant. If velocity is changing and it'll somehow be apparent in the problem, it's not appropriate to use this equation. You'll have others, don't worry.
I have a question.
Yeah.
Like the delta, how did the delta x turn in? Where did the Vx come in, and where did the delta x?
So these are our two equations for velocity, right? We have the average velocity and we have the instantaneous velocity. So what we did here is write this delta x explicitly as final minus initial, and then we took that and put it back in that formula.
Oh, okay, I see.
So this equation here is exactly this equation here with the displacement written out explicitly.
I see. Okay, thank you.
So the rest of your equations are going to be derived in this manner, with one equation subbing into another and writing it explicitly, and we'll get there. I think I still got a little bit of energy in me, but let me put a one timer on at least, and then we'll take a break at some point, maybe in 15 or so. Okay, so let's try a word problem with this equation. A kinesiologist is studying the biomechanics of the human body. Kinesiology is the study of the movement of the human body. Notice the connection of the word kinematics. And this is so true. All of the kinesiology majors have to take biomechanics, which is a fancy word for physics. And when I taught at Pepperdine, I was like helping all of them would come and ask for help, and their class was called biomechanics, but it's physics. Because it's the study of motion, right? Kinematics. Okay, so this kinesiologist, she determines the velocity of an experimental subject while he runs along a straight line at a constant rate. Okay, so let's keep reading. The kinesiologist starts the stopwatch at the moment the runner passes a given point and stops it after the runner has passed another point 20 meters away. The time interval indicated on the stopwatch is 4 seconds. So they haven't asked us a question yet, which is good because we need to really kind of figure out what all is being said here. And Nathaniel, if we have kinesiology questions, we're coming your way. Okay. So first, she's determining the velocity of a person who's running along a straight line at a constant rate. So this is part of our clues. Straight line means we're in our one dimension, and a constant rate means a constant speed. So the kinesiologist starts the stopwatch at the moment the runner passes a given point. So you have some runner. I don't have any kind of a shading here, so you can't see the depth in the forward and the back arm, but this is the runner. And then he's going to pass some point, and she starts the stopwatch at the moment the runner passes a given point and stops it after the runner has passed another point 20 meters away. Okay, so then the stopwatch, this is the stopwatch, starts here. I'm just going to call this, this is a bad stopwatch, so I'm just going to make it bigger. Anyways, So this is, oh, I made it worse. Okay, that's the stopwatch. The stopwatch starts here, and this is our starting point. And at 20 meters away, the stopwatch stops. Just the time stops, not the runner. The runner keeps going. Let's be clear and have him keep going. And there's like his little, the wind behind him running. Okay, and so at this point, we know that 20 meters have passed, and we know that the stopwatch read 4 seconds. This is all that happens from here to here. The runner was moving before, and the runner continues to move. I think we're all okay there. Okay, so from here, we can start to pull a lot of information, right? And let's see what the question is. What is the runner's velocity? Okay, so the runner's velocity here, from just the point indicated, we need to use our equation x final minus x initial over delta t. The good thing is that we know our delta t was that increment of time, 20 seconds, and we pick our final minus initial, right? And so since we're only given this information, it's probably best to say that this is final and this is initial, right? And so here's your runner's velocity then. The displacement of that time interval that they gave us, 20 meters minus 0, and we started the 0 at where they picked the stopwatch was starting, and that interval was 4 seconds. So this one seems kind of straightforward, easy enough. Remember that they were moving at a constant speed, so the average velocity equation is the same as this equation, which is why, you know, this notation, do you guys see that? Do you guys see anything? No?
No.
Oh, okay, I just got Adobe telling me to stop using it. Oh, how do I get back? Okay, I should uninstall it, right? Yeah. Okay, so that's why you see this notation, our v sub x here. Now, given everything that we have, look at what we just solved for. We just solved for the constant speed. That speed that was constant, no matter what interval of time we look at, because we know the runner is moving at a constant speed, this is going to stay the same. Okay, so let us go to the next question. Where's my little, oh my God.
It's not there.
Yeah, it's not.
Maybe you could draw it and then use it.
I think because that window popped up there.
Oh, there it is.
Yeah, I put PowerPoint back as the main screen. I had the Adobe window popped up and said to uninstall. Okay, so given the information we have now, let's solve for this problem. If the runner continues his motion after the stopwatch is stopped, what is his position after 10 seconds have passed? So I'll take you back to our image. What is his position?
50.
Position is x, some sort of x, and we're going to call it x final, after 10 seconds have passed. So delta t equals 10 seconds. All right. And just to be super clear here, oh God, there it goes again. Here. So the runner keeps going, right? It keeps going here. And it says, now 10 seconds have passed. We know that in that increment of time, we measured 20 meters, but now they want to know how much more after this 20 meters, how much more, what's its new position going to be?
So is he running 10 seconds total or 10 seconds in addition to the 4 seconds? So 14 seconds total.
14 seconds total.
Oh, okay.
10 seconds in addition, but we do not care about the 14 seconds total because the time period before, we don't need any of that information. Notice the way they state the problem. Continues his motion after the stopwatch is stopped, right? What is his position after 10 seconds have passed? So we only care about these 10 seconds that have passed. So we start a brand new time interval at where that stopwatch originally stopped on the picture. And what was our final now kind of becomes our initial, right?
So they want to know his position relative to the old endpoint.
That's right. So that's our new, what was our final now becomes our new initial. And you really want to make sure you get this, right? Because you really want to make sure you get this because the wording can trip you up. Someone might use 14 or might add in that 20. But it's all in the wording, unfortunately. And notice again, what is his position after 10 seconds have passed? So let's see. We know the velocity. We know our new fake starting initial, and we're looking for that final. So we can use our kinematic equation that we came up with. Our delta t here is going to be that 10-second interval. Our velocity is that constant speed that we calculated. Our new initial starting position is our new initial position, which was originally our final after the stopwatch is stopped. So we know this is to be 0, and we are solving for this x final. This is a typo. The equation continues from here. So x initial here is 0. Our velocity is 5 meters per second, and our time is 10 seconds. And so yes, many of you here in the chat got it, and Luis backtracked to 50. Very good. And again, it's all in the wording of the problem. So notice that I bold and underline a lot of things just so that you can to help me to really understand what it is they're asking for and what it is they're solving for. Okay, so that's our use of one equation. Now, to get into the rest of our kinematic equations, we need to go beyond a constant velocity. So in this situation, I gave you guys that scenario of your car cruising down the freeway and it's moving at a constant speed. But what if now you decide to exit the freeway? Your speed slows down and you realize, oh no, that was actually the right freeway I was supposed to be on, and you slow down a little and you get back on the freeway and you accelerate again to try to, make up time from that mistake. So now we need to look at what happens when velocity is changing over time. So first we look at position and how position changes over time, and that gives us velocity. Now we're going to look at how does velocity change over time. What does that give us? Our next one, ta-da, is the acceleration then. And you guys know this as when you're accelerating in a car or decelerating in the car and you're pushing your foot down on that gas pedal. You want to change your speed over time and not keep a constant speed. So the velocity of the particle changes with time. Exactly what it says here. V is going to change with time t, and it will result in the particle accelerating. And so here's our visual for that. Here you have your initial time and your starting velocity, and notice that the car is changing velocity. That's what this this little drag picture it's speeding up, let's say. So over this time interval, you will have a different velocity, and so that velocity can then be plotted on a graph just like we did with the position. So now we plot this on the y-axis just like we did the position, and we plotted versus time. Before we had a position time graph. Now we have a velocity time graph. But all of the math that was true for the position versus time graph is now also true for the velocity versus time graph. In that, if you want to look at your change in time, you're looking at how this changes on this x-axis. What is it? The run. And then when you look at the change in velocity, you're looking at how that velocity changes on the y-axis, which is your rise. And so again, we have the slope of the line ratio is equal to this change of velocity over change in time. I hope that's okay. And we pull that over, right? So what does this lead to? It leads to a very similar equation to our average velocity, but now we have our average acceleration is defined as that change in velocity. And notice that these x subscripts match because they're in the same direction over the change in time. And then explicitly, this is x final minus vx final minus vx initial divided by that change in time. Let me just figure out the break. Yes. Okay, so now what are our units here? Any guesses? What are our units here?
Meters per second squared.
Man, Randy, you're so fast. I could see other people reaching for the mute or probably typing out there. Yeah, meters per second squared, because this is meters per second and this is seconds. So yes, our answer here, our dimensions for acceleration are meters per second squared. And what I think is the thing you really want to understand here is that you're looking at how something is changing over time. How the position changes over time is your velocity. And then a second step, how does that velocity change over time?
So it's like in every second, it's increasing by this amount of meters per second.
Yes, that's right. That's exactly right. Yes. And of course, you can see that there's this relationship here, right? Exponential relationship. But here's a question for you guys. What if our velocity is constant? What is the acceleration?
0.
Ah,
As long as it's still going in one direction, it's not turning.
that's correct. So it's, yes, all of you in the chat too, Daniela, Saja, Mehmet, Luis, Jose, yes, it's 0 because this solution up here would be 0. And also physically, if you think about this, you know, you're not accelerating or decelerating with the gas pedal when you're on cruise control on the freeway, or I don't know if people still use cruise control, to be honest. But let's say, oh, you do. Okay.
They use autopilot now.
Oh, autopilot, yes. The Tesla. Or let's say again, you're just the flow of traffic is just moving, right? Think about physically, you're not actually accelerating with your gas pedal. You're keeping that speed constant, and so the velocity, if the velocity is constant, your acceleration will always be 0. Yeah, cruise control for really long stretches. I agree. Okay, so this average then will translate over to our instantaneous values, and we can make the same exact relationships we did from position and velocity and average velocity and bring it over to instantaneous accelerations. So sometimes the value of the average acceleration, of course, the average acceleration may be different over some time intervals. And so if the average acceleration is changing, we want to look at the instantaneous acceleration. And we want to do that same thing that we did before, where we are going to minimize this time interval from a large gap that we would use to look at an average to a much smaller time interval that approaches as close as we can to 0. Okay, after this, we'll talk about a break. Yeah, so our limit of the average acceleration then as delta t approaches to 0, you're going to see is the exact same is the exact same thing as when the velocity, when we're looking at the instantaneous velocity. So we look again at the slope, right? From A to B, the slope of the line here is going to be this blue line. And what if we want to get closer and closer to B? You know, you start changing up this line here until eventually you look at this small time interval here. And this is the time interval I'm looking at. Oh no, and it's supposed to be a, you know, a bar. Very small time interval that has at that point in time that slope of that line. And so our instantaneous acceleration again is the limit as that delta t, that time interval, gets closer and closer to 0 of the ratio of the velocity over the change in time. And this is the derivative of the velocity. And again, I like to write it like this just to keep things organized so that I know what I'm taking the derivative of. This then will go, let me go 2 more slides to make sure we complete this thought out. And so this is our acceleration. And, you know, again, we're taking these steps in time. So you could compare the 2 graphs, for example, the velocity versus time graph. And every time you take the slope here, the value of this slope will be the same value of the acceleration at that position in time. The value of this slope, what is the value of this slope, everyone?
0.
It's 0. The value of that slope will be the value of the acceleration of that time, right? This is the derivative. This is the delta V over delta T. And look at this one. The slope here is downwards. And so the value of this slope is the value of the acceleration at that time. And it in fact matches it because it's in a negative, it's decreasing, right? So the acceleration at any time is equal to the slope of that velocity time graph. Many more kind of math connections that we can make here with using the slope. But again, it's kind of supporting what we see physically with what we see mathematically. And so from here on out, anytime we say acceleration and velocity, we're always going to mean the instantaneous of those values. We start off with the averages just because we want to get comfortable with it. But in physics, you know, it's what Randy said earlier, we're not really interested in estimates. We're scientists. We can get to these very specific values. So in our everyday use of the word in this class, every time we say acceleration, we are talking about instantaneous acceleration. And if we want the average acceleration, we will say or denote it with a subscript, the word average. And then the last notation again, this acceleration that we are talking about is the second derivative of the particle's position with respect to time. And it's so cool because you're taking the position, dividing it by time to get velocity, and dividing it by time one more time. If for velocity, oh my gosh, dividing it by time once more to get acceleration, right? And those are for averages, but for our instantaneous values, this is what they then look like. The acceleration is the derivative of the velocity, which is the derivative of the derivative of the position's derivative with respect to time. And this is again why I like to write the parentheses next to the derivative. Because then I know exactly what it is I'm deriving. And so this double derivative this is not a squared, this is the second derivative. And you can absolutely write this out as x prime. And you can write this one out as x prime and x double prime. And I'm gonna throw it out there for you guys. If any of you are going into like mechanical engineering or maybe even civil, pretty soon you're going to start taking derivatives instead of with respect to time, with respect to position instead. And you're gonna have to differentiate that with like dots, right? X dot and X double dot. That's what's coming in like a year or two. In a few classes, this is what you're going to see. Yeah, but it'll be okay, you know, it's not so bad. Okay, so this sums up our definition for acceleration, and perhaps we can try. You guys got about 5 minutes in you before we take a break?
Sure.
Yeah. Okay, I'll take that. Okay, sounds good. Okay, let's just try one problem before we try everything. Yeah, and okay, and I see the thumbs up, thank you. Okay, so let's try this problem then. The velocity of a particle moving along the x-axis varies according to the expression Vx is equal to 40 minus 5t squared, where Vx is in meters per second and t is in seconds. And so notice again, Vx is on the y-axis. Oh, my chat is in the way. T is down there somewhere. I can't actually see the t, but you guys can. T is the time is on the x-axis there. And so we see our graph is this red line and points A and B, and there's a slope line there. And at just that point B, which is at 2 seconds, we see a slope line there too. Oh, I think it says it there too. Yeah, which is negative 20 meters per second. Oh, okay, nice. Okay, so let's go for our first question then. Find the average acceleration in the time interval. So this might seem like a little bit of a drag now that we have to do averages still, but it's just to practice, right? So what is the average from t equals 0 to t equals 2 seconds? So we want to find that velocity at 2 seconds, find that velocity at 0 seconds, and subtract the 2 and divide it over time. It goes with our equation, right? So here's our velocity at A and our velocity at B. And I might have said that too fast, so let me just write it out, right? A average is equal to delta V over delta T. So to get this delta V is VB minus VA, and that's what we're doing here. So we took the equation, we didn't do any derivatives of any sort, and we're just gonna plug in the values for T at A, which is 0, and the value of T at point B, which is 2. And now we use our average acceleration equation in terms of the variables given in the problem, and we plug them all in. And so look at what we get here. 20 minus 40 over 2 seconds is negative 10 meters per second squared. So the average from A to B is this blue line, which also has a slope downwards, which does give us this negative. And so physically this matches. Anyone out there wanna get the instantaneous value here? I mean, they give it to us, but can we prove it?
So we would do like the 3, I guess. The 3 as the time, and then as the final time, and then the initial time as 1. So over 2.
What? Why are you saying 3 and 1?
Because I'm looking at the graph and it crosses the 0, 3 point.
Oh, you're using the slope.
Yeah.
Yeah.
Oh, we're not using the, sorry, I forgot to use the derivative.
No,
Does
it's
it give us-
okay. I was asking because there's no question after this on the problem, but I was just asking out there for you guys, can we do a quick derivative and get the, I mean, the answer is on the, on the thing, but this is what it would look like, right? But
Where is the equation for it?
I wrote it right here.
That's, oh, okay.
Okay. Yeah, and so the acceleration then is d of dt of v, right? And
So that's 10t, negative 10t.
Is it 40? Well, 40 goes away. Yeah. I need you guys to have to remind me of this. What was it? Negative 10t?
Yeah.
Okay, negative 10t, and we plug in our 2 seconds, and it does in fact match what is set up there. So you guys can see that we can get the average acceleration. Look, Nathaniel, wow. Yeah, he wrote it all out. And yes, Noah, it is the same. And I see Jose and Owen got the answers out there too. Oh, Luis. He says, what does the third derivative give us? Well, the third derivative, yes. So the jerk is the mathematical answer. And in physics,
Torque, no?
No, not exactly, almost, but not close to it. We have to take an extra step before we take the third derivative and have it physically mean something. Owen says acceleration. Yeah, so I'll give you just a sneak peek, but the next set of the derivatives that we would take would not involve just the acceleration, but the force. And the force has the acceleration in it, F equals ma. And so the third derivative would then involve the force, and it would be the impulse. And so the answer
would be
the impulse. And a quick way for you guys to remember what is the impulse is, imagine when you're in a car and you have the seatbelt on and it comes to a sudden stop, and you're accelerating, moving, all of that, and you suddenly have a huge jolt, right? And that jolt can be graphed out like this.
How is that related to like inertia, or is that like change in inertia or something?
Yeah. Eventually in rotational motion, we can also relate the force changing over time as an impulse. We can relate that to inertia also. It's easier to do it with torque, which is what you were talking about with rotational motion, and we will do that. We'll see it a little bit in 101, and I'm not really sure if we'll get to it in detail. Yeah, impulse and momentum, that's right. Someone was asking me impulse and momentum, and the way we bring in momentum in this class in detail, not just in collisions, is through rotational motion and torque. You'll see a little bit of it though. Okay, so this is all great. I'd like to, I think we should take a break, and then we'll start again with our motion diagram. And after this, we will derive the rest of the equations. And I think we have enough time to do a problem. Yeah. Okay, I see a break's good. 11:30, is that okay? It's 12 minutes.
Fantastic.
Okay. Let me see if I can do this pause sharing. I don't like that. That looks weird. I'll just stop sharing. Okay, so I see thumbs up. Thank you guys. I'll see you at 11:30.
See you then.
I'm back. Hi, everyone. I hope you're all here.
Hello.
Hi. Hello, Keon. Hello, Randy. Hello, Alyssa.
Hello.
Hi. I hear all you guys too. Hi, Jonathan. I see you all back. Hello, Alexandra too. Oh, and Daniela and Jonathan. Hello. And Owen. So, welcome back from our short break. We're going to finish up on chapter 2 and derive the rest of our equations. But before that, we have one of our tutors from TradeTech and one of my past students who has been in so many of my classes before. Yeah.
Oh, I know her.
Yes, you do know her, Randy. And she's here to tell you all about Academic Connections, the tutoring at Trade. So please, if you have any questions, feel free. Alyssa, should I share the flyer?
If you like, yeah.
Okay,
So everybody can see it.
I'll do it for just a few minutes until all hell. Okay, I found it. It's all good. Okay, Alyssa, the floor is yours. Welcome and thank you for being
Hold on a second.
People in the chat say hello. Oh no, can you hear us? Maybe? Test.
Hold on a
Alyssa.
second.
Hi.
Okay, can you guys hear me?
I can hear you.
Okay, wonderful. I had to reset my headphones. Good morning, everybody.
Buenos dias.
Okay, so I am one of the tutors at LA Trade Tech's Academic Connections Tutoring Center, or just Tutoring Center for short, but they have me say that whole part. So we're open during the winter right now. The hours are, as you see, it's from 8 a.m. to 6 p.m. Monday through Thursday. And I'm not sure if any of you guys have gotten tutoring before, but it's free. It's one-on-one, it's online, it's virtual, and it's for a wide range of topics. So maybe you might not need tutoring for this class, but you might need tutoring for another class. The only requisite is that you need to at least be taking one class at Trade Tech. And then any other classes that you might be taking somewhere else, you can still receive tutoring from us. So there's a lot of ways that you could get into contact with us. You can call us, you can text us, you can email us to schedule an appointment with a tutor. And most of the tutors that will be available to tutor things like physics and yes, you've had Vasily. Yes, he's a great physics tutor. All of us have taken classes with Dr. Klee at some point. So our goal is to make sure that you ace your classes and, just make life a little bit easier for you. Any questions?
I also think Vasily is awesome.
Vasily is awesome.
Any comments, questions? I guess a question, Alyssa, what is the first step to getting tutoring at Academic Connection?
The first step is contacting us. So from there, it's just as simple as like my name's Alyssa, I would like to receive tutoring in this subject. The people at our front desk will guide you through the process there's just a simple form that you have to fill out, and then you can get into contact with a tutor in your subject within minutes. Or you can schedule it for ahead of time. Let's say you need tutoring not today, but tomorrow. I highly recommend that you schedule ahead of time, but tutoring is just getting into contact with a tutor is really quick and really simple.
Yeah, I agree. Whenever I'm gonna stop sharing the screen, but I will put that link for you guys just so we can all talk. I mentioned the other day that if you ever have any issues with getting in contact with anyone at Academic Connections, that you could email me. And what I would do is contact all my tutors, contact all my students. I would contact Vasily, I would email Alyssa, and they will get you through it right away. So, and again, all of the physics tutors are pretty much students that have taken my classes and all of the other engineering and math classes available at Trade. So really experienced people. And just this past year, Alyssa and Vasily have transferred out. So
yeah, I'm attending Dr. Klee's school at UCR.
Yeah, my PhD school. Hey. And Vasily at Irvine, is that right? Yes, Vasily at Irvine. So yeah, Randy, you had a hand up.
No.
No? Okay. Oh yeah, I went
We
back.
we accept tips. I'm just kidding.
Yeah, Randy's an English tutor at Academic Connections.
Oh,
so-
Randy, hi. How are you doing?
Pretty good.
I recognize
Maybe
you.
someday I'll be over on that side if we ever get
You
back
should. We
into
would
the building.
absolutely welcome you. Absolutely.
You would be. So again, any comment, questions, anything at all for tutoring, I highly recommend it. Sometimes you can certainly use tutoring services for figuring out homework and lab, but sometimes you might just want to know how to get by in a class and how to figure out, the load of your classes and how to study and how to handle the anxiety that comes with taking these classes. And again, all these students have taken these classes. So, yeah.
If anybody knows what you guys are going through, it's definitely us tutors.
Yeah, it's true. Andrea, you have a question if you'd like to unmute or chat.
Hi, I have a question about can we go to the tutoring without an appointment?
Without an appointment?
A drop-in?
You still have to set up an appointment. You cannot meet with a tutor without having first gone through the front desk saying, I would like to meet with this tutor, and them confirming it with you. Because if we don't see it on our side, on our little schedule, who we're going to be tutoring that day, we cannot tutor that person. But you can still do a drop-in and get to see a tutor immediately, but you still would have to essentially make that appointment. It's an immediate appointment.
Yeah.
Oh, okay.
It's as close as we can get to a walk-in virtually, because on campus, you would be able to just walk in. And on campus, I would walk through and say hello to all of you too.
Yes.
I'm very happy when you're there.
So I do recommend, though, setting your appointments for the future, because the problem with drop-ins is that you might not get the tutor that you like, or you might not see any tutors available for the subject that you need to get tutored in.
Yes, all of that's true too.
Approximately how many of you guys are able to teach this subject that we're taking 101?
Let's see. We have...
Is it almost all of them? Say Math 125 is pretty much everybody.
Yeah, Math 1. Yeah, that is pretty much everybody. Yes. But the best would be Vasily, and I highly encourage you to seek him out.
I thought they just said he wasn't no longer there. He graduated.
Well, Vasily graduated, yes, but he's still working at the tutoring center.
Oh, yeah. Okay.
Yeah. And myself, Vasily, Jesus, we've taken all the physics series with Klee. So although everybody has the capacity to tutor you in the physics subjects, there are some of us which might be a little bit more, adept with Dr. Klee's style and familiar with the subjects.
Okay.
And I'll add that the name she's been saying, Vasily and Jesus, they're continuing their study in physics, now transferred out. So, yeah.
Is Vasily the really tall guy? He's
the
really
Russian
tall
one.
one. Oh,
Yeah.
the Russian. Okay, yeah, I remember.
Really tall, but don't let his tallness fool you.
He's 17.
He's a youngin'.
Oh my God.
I know.
And then, so another question I have, I've never made an appointment with you guys before, but so what's the process? Say if I think I'm going to need you, and so I schedule you, but then I don't actually need you. Is it best for me to then, instead of cancel, to come to the appointment and say hello and then say, oh, I don't need you, I'm done? That wouldn't count as a cancel, whereas you guys would continue to schedule me? Or would I just best just schedule just before?
I would highly recommend, if you know that you're not going to need the tutor, that you cancel the appointment. It's such a quick, simple text that you could send, and what that does is it helps us tutors have more open slots available for other students who might need the help.
Okay.
Because that doesn't get erased from our sheet, and we can tell the front desk, hey, my student left early, I have an open slot available, but it's just a little bit more effective if you guys just send us a quick text saying that you're not going to be able to make it to the appointment.
Okay.
Does anybody have any questions? Any other questions? Any questions for me personally, being somebody who took all of the physics and all the engineering courses at Trade Tech?
I have one.
Yes.
So I was asking Dr. Klee about this yesterday. and the day before. So would you compare like the number of hours you spent on, say, Calculus 1 to the number of hours you spent on Physics 1?
Everybody has their strong suit. My strong suit just happened to be math. As much as I hated it, I was pretty okay with math. And I still found myself having to spend an equal amount of time in all of my classes studying and preparing for them. Because as much as you think that you are good at something, the fixed mindset works both ways. You might, I'm hoping most of you guys know what a fixed mindset is.
Yeah.
So you might think that because you're bad at something now, you won't be good at it later. But there's also that fixed mindset that nobody talks about, that feeling that you are already as good as you can be now and that you don't have any further room for improvement. So think that in itself is also a fixed mindset. So even if you think that, oh, I don't need to spend that much time on calculus because I'm good at math, or I'm already taking physics 11, I should be okay with physics 101. I highly discourage you to do that. Spend as much time as you think is not necessary. Like, just become immersed in these subjects. You need to become this perfect vessel to receive this amazing knowledge that you're going to be given by Dr. Klee, Dr. Navarro, all the calculus professors. There is no right or wrong answer to how much should I be studying for this. The answer is technically no, you're not studying enough.
Like, I mean, as far as the physical homework, like I know my calculus class took like pretty much like 90% of my time on that, just doing the homework. Whereas like, and that wasn't like studying, that was just doing the work that has been assigned. Whereas my other classes were like 10% of my load.
Yeah, that also depends on the teacher that you're taking for calculus, because the professor that I had, Miss Lopez, she assigned homework up the butt. But I see what you mean. And that,
like,
unfortunately,
so far physics seems a little less like labor intensive, like as far as like the number of problems, but that could just be where at the very beginning, you know?
Well, if you're just looking at homework, then yes, Dr. Klee doesn't assign as much homework as a calculus professor, but that means that you're probably not spending enough time studying for Dr. Klee's class.
Okay.
Just homework is definitely entirely up to the professor how much they want to assign it to you, but you should, aside from your homework, spend the right amount of time studying for each class. I think it's 3 hours per unit or 3 hours per hour lecture, something like that.
Did anyone else have a question? I thought I saw one or two unmuted.
Do you guys offer help?
I was kind of wondering, oh, hello. I was wondering what was the common times for, the best times, let's say, to come in for tutoring?
Best times? Best time is whatever works for you. We're always scheduled so that there's a tutor that all subjects are available at all times. I suppose mornings would be best because not a lot of people come in the morning, but then again, not a lot of people are awake in the morning. There's no right or wrong time. Just come on in and try and schedule as ahead of time as possible. So that, and if you guys, the standard amount of time to spend with a student is between 30 and 45 minutes. But if you guys feel that you're going to need more time with the tutor, say that ahead of time. Just say, hey, I know we're only allowed this allotted amount of time. Is it okay if I get an extension afterwards? Or if I book a double appointment with the same tutor? Things like that. And I see a question. You're welcome. I see a question if we offer help for STEM internship applications. The tutoring center does not, but there's a lot of resources that Dr. Klee and Dr. Navarro have set up. There's a Discord for STEM in trade tech, and I'm on that Discord. If you guys ever need help with that kind of stuff, I'm there.
Yeah, we used to do this a lot through our STEM club, and we're kind of rearranging the STEM club before we bring it back virtually. But for now, you can ask any of your faculty for help. And last semester, I was helping up the yin yang with applications, and I'm very happy. I got 2 students into the NCAS, the NASA Community College internship. So one from Physics 101 and one from Physics 102. Yeah, so any help you need, always happy to help with anything. Yeah, and when I do hear about things, I'll put them on our Canvas page too.
Oh, I have a quick question as well. I was wondering how.
Oh, Alexandra, you're muted. Come back.
Oh, I'm sorry about that. I was wondering like how many classes you're taking with like your physics, like your physics classes as well.
I'm majoring in mechanical engineering. Lucky for me, all of my physics classes transfer. I no longer have to take any physics classes at UCR. However, all the knowledge that I've learned in my physics classes, I still use them on a day-to-day basis. All my notebooks are to the side over here of all the notes that I've ever taken at Trade Tech because I still reference them and I use them quite a bit. So it's not that I'm taking physics classes right now, but everything relies on that foundation. So it's not something that, oh, I already know it. What's the next subject that I need to learn? It's something that is constantly being applied in all of my classes.
Did you take physics 102 and physics or in calc 2 together? Like, did you take all these 3 classes at the same time, like with one another?
No, actually, I was one class ahead in calculus than I was in physics. So when I was in physics 101, I was taking calculus 2.
Okay. Do you find that that was like doable for you to have the physics next to the calculus and it worked?
Yes.
Like it wasn't too much? Okay.
Actually, it kind of helped that I had a calculus class. I was a calculus class ahead because I already knew the necessary calculus that I needed to know in physics. So if a lot of calculus professors might be a little bit behind in teaching you derivatives. And if you already need to know derivatives by the time that you're taking, by the time you need it in physics, then it helped that I already knew everything. And it also helped that if I felt that I was going to fail a calculus class, that even if I failed it, I wouldn't have to worry about, oh, I can't sign up for physics 103 next semester. Not that I ever did, but it did kind of help to be a little bit ahead of the game. It was absolutely manageable to take the 2 classes at the same time, although I did not have any social life.
Yeah, I understand that.
Yeah, that's the normal schedule or typical schedule for a STEM student that's going to school full time. In the beginning is usually to have a calculus and a physics class. The second semester, we start to have you add on more classes. And eventually you're going to get to the point where your whole load is all science classes and maybe one fun class like like an art class or a PE class or just something fun like a seminar on the environment or something. So the goal is to get used to this and take on that challenge and prepare for that challenge. Yeah.
And it is a challenge. Don't take 18 units on your first quarter like I did. That was a terrible idea.
Yeah. Okay. I think we have.
I have one more question about the tutoring thing.
Yeah.
Like, do you ever do multiple on the tutoring center, you go in and there's multiple people together and they're like all seeing the same board because they're working on the same subject?
Mm-hmm.
Is it like a room like that kind of in tutoring ever? Because that's kind
very rare that we actually get group appointments, but we absolutely love group appointments. They're possible. You just need to tell the person who is also going to be with you in the tutoring, same tutoring appointment. They also have to go through the same process of filling out that simple little form so that they can receive tutoring. And then, you just relay that to the front desk, like, hey, me and this person are already signed up for tutoring and we would like to have a group appointment with this tutor. Not only that, but there are some cases in which there's more than one tutor in a group appointment. So if you and a couple of your buddies from this class want a group appointment, me and Vasily would both be helping you guys. So it's an incredible experience to be collaborating like that. And it's entirely possible, yes.
Thank you.
Mm-hmm. Any other questions?
So I think because
no more questions.
Yeah, we need to lecture. We need to go back to physics. But maybe in the future we could have you come in again, Alyssa. Or it'd be nice to have you come in maybe 4th week or something, and Vasily too, and maybe even Jesus if he's free too. And the next thing I'll say is that all these questions, any of us are always able to help you with, and if you have time, Alyssa, if you could put the Discord link in the chat. If not, I'll put it in the chat or I'll send it out to our Canvas. But it's a Discord for engineering STEM majors, and we have quite a few alumni on there also. So yeah, check it out. Yeah. Okay. That's all I got.
All right. Thank you, Dr. Clay.
Thank you, Alyssa. Always appreciate it, and do good on the quarter system. It's okay.
Yes.
You will see the light. You will. Ask Alexis. He knows.
All right. Thanks, guys, for having me. Bye.
Okay. Thank you, Alyssa.
Hi, thank you.
So guys, if you ever have any other questions about tutoring, again, I'm happy to help. We have a lot of people in our class that are knowledgeable about the resources at Trade and just in general about any other resources for science and learning physics. So please, feel free to ask. This is a good place and a good group to help with. Yeah. Okay. So, and thank you all for, being active while Alyssa was here to talk to us. They don't have to come to visit our class, and it's nice that they do. So go visit, we'll have a one-on-one, it'll be helpful. Okay, I'm gonna get us back into our chapter 2 and finish our motion diagram lecture and that part of physics. And I think all we'd have left after that is to derive these equations, and hopefully we'll have a problem or two to practice. If we don't get to the practice problem, we'll just start on it first thing tomorrow. And then we will talk tomorrow in detail about the exam at the end of class. So hold your questions. Well, then I promise I will tell you in detail so that you feel comfortable starting the exam at least, or preparing for it. Okay, so let me switch this back over. I hope you can see my slide now. Let me move my screens around. The sun decided to come out, so I'm getting blinded in different directions here. Whoa. Okay. So we finished with getting our last equation, right? Let me just go back a slide. With the acceleration being the derivative of the velocity, and if something is changing over time, we get the velocity. If the velocity is changing over time, we get the speed. And so you can see how you can see some of these changes with these motion diagrams and using these arrows here. So looking at this first car here, you see that the car is moving at a constant speed. The reason we can see that is because the car and the moments that we're kind of measuring, its position over some time, these are equally spaced out. So we can make that assumption based on this picture that the position is changing at the same rate over the same interval of time. Let's say 10 seconds. So every 10 seconds, we see the car moving with the same amount of position every time. So it's displacing at the same rate. And we see that the velocity here is displayed by this arrow, and next chapter we'll use these vectors. You see that the arrow is pointing in the same direction for each car, and the length of the arrow is the same for each car. All right, so what if then we change the velocity of the car? What if then it's perhaps starting off at a lower speed, and notice that this lower speed is indicated by a shorter length arrow, and in some interval of time that we're going to say is equal, we see that that arrow starts to increase, right? So the velocity is increasing over that same interval of time that we're measuring, every second, every 10 seconds perhaps. So you see the arrow increasing, but now because the velocity is changing over time, we have an acceleration. But in this situation, notice that the acceleration, the arrow is pointing all in the same direction, but it's staying the same length. This is indicating to us that the acceleration here is constant. Because the acceleration is constant, it does not always mean that it's zero. It could be zero, but it could also be a constant acceleration of, I don't know, 2 miles per hour or 2 meters per second, which would mean that every second we're increasing by another 2 meters per second. And so here you see the velocity arrow increasing while the acceleration is moving in the same direction and staying the same rate. Another way to say this is that the velocity is changing with a constant rate. The velocity is changing by a constant rate. So we still see that change. Now here's one to kind of get us into the what about if we're slowing down? What might happen then? Um, so here you see the velocity starting with a larger speed, again with the longer arrow, and over those same little intervals of time that we're measuring, the arrow gets smaller and smaller and smaller, and this tells us that we're covering less position, less ground in that same interval of time. If you cover less ground in that same interval of time, you're slowing down. And so the acceleration vector here is going to point in the opposite direction. It doesn't necessarily mean it's a negative value. It could be a negative value. It could be. It doesn't have to be. But it's just telling us that we are going opposite of the velocity's direction here. So we are slowing down. And Nathaniel says a negative slope. Yeah, this is how we would see that negative slope, downward slope. And this is what we would call everyday language decelerating, right? We're going to slowly, your acceleration is now slowing down, or it's decreasing. What other way can we say this? Yeah, those are yeah, you can say this instead of saying negative, you can always say slowing down, you can say decreasing, but the negative is indicating some opposite effect
Could it
to
be
the velocity.
could it be
Yeah?
like so could it be like a left turn, like turning left, because like left would be the negative direction?
Yeah, it would be like as if it was going to oppose the direction that you were coming, right? So if you're driving straight and now you face a really strong wind coming opposite of you, then that would be it. Or if you're going to make a turn and slow down because you're making that turn, yeah, you could say an opposite direction, left to right, north to south, west to east. Something is opposing it that's going to cause you to slow down. Yeah.
Like
So
wind resistance or the brakes, right?
yes, like wind resistance or the brakes that will decelerate us. And so this is one way where you're going to see the acceleration going the opposite direction. Sometimes you might see a slope that's more, what's the opposite of steep? Less steep, right?
Lesser grade.
Yeah. Oh, lesser grade. Thanks, Randy. That's a good one. Yeah. Something more slow, something more, yeah, something more shallow.
Gradual.
Gradual. You'll see a change in the slope. And so it might not be negative, but it'll show us that like, for example, this is a really a fast velocity, but at some point the velocity or the acceleration might change and have a slope like this, right? So this is a slower increase. It's still increasing, but it's a slower one. And so then here you would have a negative and also considered also a slowdown, but this would be leaning towards the opposite direction. So here you really want to, let's see if we can maybe try a question here. This one might be tricky, but let's try it. Which of the following statements is true? If a car is traveling eastward, its acceleration must be eastward. If a car is slowing down, its acceleration must be negative. A particle with a constant acceleration will never stop and stay stopped. Any ideas? Only one of these is absolutely true. And you could use the last example that we just did to help answer some of these. Let's try this one. If a car is traveling eastward, must the acceleration also be eastward?
No.
No.
You can say it's relative to any direction.
You could say it's relative to any direction. And just like the example we just saw, we could be traveling eastward, but we could be accelerating to the west, right? Which is a deceleration, like if a wind is hitting us. Now, okay, I see different groups of answers. This is good. What about B? If a car is slowing down, its acceleration must be negative. I actually just drew this it's right here.
Yes.
Right? So this is fast and this is slow. Do we at least agree with that statement? One is faster and one is slower. Yes. Now, do we agree that both of these are positive? Yeah.
Yeah.
So, what happened? Oh, it's because I actually, I was gonna skip that question for time, but yeah. So if a car is slowing down, its acceleration does not necessarily have to be negative. It could just be slowing down in a rate that is still within that positive range. And it really depends on the situation and the scenario. On the graph we saw earlier, you could, yes, Daniela, that's exactly it. It does depend on our reference point, because on the graph we saw much earlier, we saw that a negative acceleration, a negative velocity yielded that negative acceleration on that graph. Yeah, okay, so this one doesn't always have to be true. Now, what about this one? A particle with a constant acceleration will never stop and stay stopped. What does a constant acceleration mean?
It could just be stopped and stay stopped because it has a zero acceleration, which is constant.
So I probably fooled you guys a little bit earlier with when I said it could be zero, but let's try this. A constant acceleration is, let's say, a number. A constant acceleration means that there is an acceleration.
So it's not zero?
Correct. In this situation, it is non-zero. Sometimes when it's zero, they'll specify and say a particle with zero acceleration or no acceleration. But if it has a constant acceleration, let's say the acceleration is 5, what could the velocity be?
Anything? Positive?
Yeah, it could be like 5x, right? Because the derivative of 5x would then be 5 or 5 quadrillion. Thank you, Owen. Yeah, if the acceleration is constant, meaning you're constantly increasing, maybe like a rocket ship, you're increasing so much over time that you're still moving. So I think the answer here should be C. Yeah. If a particle is constantly accelerating, it will never stop and stay stopped. And another way to prove this to yourself is to look at the equations. And this one here is the key to this one, is that you're always moving over time. For this to equal some sort of number, right? And time is not zero, we must have a number right here. We must have a change in position of some sort. Can you please explain why B is incorrect again? Yes, I'll go to that. And can it be a negative constant number? Like, can it be -5? Yeah, it can be like a -5 because that negative is telling us something about the direction. And let's go to B again. If a car is slowing down, its acceleration must be negative. So this is the graph that I drew earlier. You could have a fast acceleration, right? This is V over T, and you'd have some fast acceleration here, or, let's just make it A for acceleration. And you could also have a car that is not accelerating at that speed anymore, right? But maybe like that. You notice how, although it's not going to go as fast as you see here, you're still going to have a change in the steepness of this slope. So the way the slope is really what's telling us how fast or slow something is going. I think I drew it on the last slide. Yes, so it's still moving, just more slowly. I think that I draw it here. Yeah, like here you have a fast increase and here you have a much slower increase. So the acceleration could still be accelerating just a little bit slower, but doesn't mean that you're going negative. The situation will arise where you can be negative. And let me show you that graph. And this was going back to, I think, Daniela's point, that it does depend on the reference point. Here we have a negative slope, and this did result in a negative acceleration, but it doesn't always have to be. And look at this one here. This is a great example. Look at the slopes here. This is a very steep slope, and this is not as steep of a slope, but it's
you
still
wouldn't you use the first derivative test or something to find out if it's negative or positive based on the concavity or if it went from increasing to decreasing?
Yeah, I think so. I don't remember those in detail, but I do think that you could use that to check the steepness of the slope. But you could also visually see the steepness of the slope, right? This one, and a good way to see it is to draw the lines out really long. So this one has a slower growth, then this one is much faster. You can even across them, and you can see it that way too. Yeah. Okay, some questions. Why not C? Can't the acceleration be 0? The acceleration can be 0, but we are not going to use that as a constant number. So when they say a constant acceleration in this situation, they mean a constant like a number here. So this is just a wording issue. And then Henry, but in both instances, the car is still speeding up, right? No, the car is still moving, but yes, you're still speeding up, but you're speeding up at a slower rate. I hope that makes sense. You are speeding up, but you're speeding up at a slower rate.
So like if you were driving on a highway and you were going really fast and accelerating really fast, but then you let off the gas, you're like still accelerating, right?
Yes, your velocity is still changing over time, but not as fast as it was before, not at the rate that it was before. And this is why I keep saying the word rate, because it's not necessarily how much position you're changing, but what is the rate of that position changing over time. So think about this question a little bit more. I actually took it out because this one tends to bring up many scenarios. But as long as you are able to connect that position over time is velocity, and velocity over time is acceleration, and you can make a relationship between the slopes there, you're kind of okay. Yeah, I think you'll be okay. Okay. But it's good to really think about this. Okay, so here is the summary of the equations that we have so far. And I'm going to show you this before we derive the rest of the equations. And we're going to derive the next 4 equations on the quicker side, and then we'll get to practice them probably tomorrow. But let me show you what we've done so far. This is a good page to screenshot. It's also on the last page of your chapter. There's a summary of equations on your chapters, every chapter. So here we have our displacement, right? Our position, change in position. Here we have our different velocities, average and instantaneous. Here we have our accelerations. And when we're moving at a constant velocity, we have our first kinematic equation that solves for the final position if you have all the rest of this information. If you have, you could rearrange this to solve for anything else too, but very nicely it solves for final position. So this is all if we have a constant velocity. What if now we look at the situation where our acceleration isn't changing, but our acceleration remains constant? If our acceleration remains constant, we can derive many more of these equations just like we did for this velocity one. Okay, so here are the first of those equations. So again, the derivation, I don't need you to know it very much, but I just need you to kind of recognize where it's coming from. All this motion, we can have several different scenarios of how things are accelerating, and it can be very difficult to analyze. Just like you guys came up with every little scenario that you could with acceleration, that'll become very complicated to create a model. So we are going to work with a simple model where acceleration is always constant. And so this is what we'll do with our equations. So we're going to start with the instantaneous acceleration, and this is our definition for that. And with this one, we are going to rearrange it and solve just like we did for the final position and solve for that final velocity. All we did was take this instantaneous acceleration, right? Instantaneous acceleration equation and solve for this final velocity. We move the time over to this side and we add the velocity over, and here is our second equation. That's pretty simple, right? Our second kinematic equation. Okay, our third kinematic equation comes from the idea of the average. Now, the average of anything is just that, taking an average of a certain amount of numbers. If I have 3 sets of numbers and I want to take the average, what do I divide that number by? This isn't a trick question. If I have 3 sets of numbers, 3 numbers, and I want the average of those 3 numbers,
3.
Thank you. I add them up and divide them by 3. That's right. Thank you. I see it. Okay, what if I have 2 numbers?
2.
Thank you. So thank you, Bradley and Randy out there too, and Keon. Yeah, so if you have an average, it really comes out to be just that. So if you have a constant acceleration, remember, a constant acceleration, we can actually, it's right here. This is a constant acceleration. At any point, at any instant of this average acceleration that's constant, the instant acceleration will equal that average acceleration. So final minus initial here, we could take any point as the final, at any point as the initial, and take them as actual points, right? So this could be v initial or acceleration initial, this, if it were the slope, and v final, any of those points as 2 points along the average. And so the average velocity is just that, the average of the 2 points. And so we can take any 2 points, the initial perhaps and the final perhaps, let's say initial here and final, oh God, final
Why
here.
why is it just T? Why is it not TF minus TI?
Where? Here?
Yeah.
Because we assume TI to be 0. We assume to start time when the situation, we just assume it to be 0, the start of whatever our scenario is. And this is going to be very, very useful to us. And we're going to try to make this as usual and as common as possible too. So pretty soon you're going to see delta T pretty much turn into T, because we're always going to try to take the beginning of time, T initial, to be our starting point, our 0. Okay, so there we have, this was our, I think our second equation, was it? Yeah, and this was our third equation now. So we took the average of the velocity that is moving at a constant rate, or the accelerations moving at a constant rate, took those 2 points, divide them by 2, because it's just that, an average, and you have a new equation for the average velocity. Now let me say this too, this equation is not as common to use. We hardly ever use this one. So just know that this is not the first equation you're ever going to go to. In fact, we're going to use this to help us derive other ones, but it's not going to be the main one. And I'll tell you which ones are the main ones pretty soon. Okay, so now we have 3 equations derived, and let's kind of remember these. Number 2 and number 3.
So 2 and 3 are both derived from the first one.
No.
No.
No, the first one is constant velocity.
Constant.
And that one's derived from velocity. This one is constant acceleration, that's derived from acceleration.
Not like, so the one at the top is not like, you didn't get the second one by that one?
I did, but this isn't our first equation. Our first equation.
No, oh, okay, yeah.
You got it? Okay.
Yeah.
Our first, and I mean our blue box equations, right?
Okay.
The blue box equations are kinematic equations. So the first one was from constant velocity. This is the second one here, and this is the third one here. So here comes our fourth one, and this one we're going to have to derive. I think I have an extra one, but that's okay. So based on the last equation, we now have 2 ways to define the average velocity. We have the equation that we're used to seeing, which was the displacement over time, and we also have just taken the average of 2 points. Using this definition, we can now derive our next equation. So the first thing we're going to do is use the position equation, displacement, and we're going to plug that into another equation. We're going to solve for position, which will be x final. Solve for, right, x final. And now we're going to plug this into, what was it? Our x average t, right? And here you now have x final minus x initial, which was just the displacement, that's it, is equal to v average times t. That came from this equation. The next thing we're going to do is take our new definition for the average velocity, and we're going to plug that in here. Okay? And this is what it looks like. So now we have this 1/2 v initial plus v final, that's here, the second equation, times time, which is brought back down from there. And just like we did in the last equations, usually what we want to solve for is the final moment of something, and in this case, the final position. So we just bring over the x initial to the other side, and here we have another kinematic equation. This one is used sometimes. Not the go-to either, but it's used sometimes.
These kind of things like come to you, right? Like they're not something you're trying to memorize. They just kind of like happen, like based on what you see you have and what you need. And
yes, absolutely. You do not need to know this derivation. I'm showing you that it comes from the beginning equations. And then these, you're always going to have these kinematic equations as a list, and you're going to compare what it is that you have and, you know, use the most direct equation from there. Okay, let's go to the next equation. Okay, the next two is just going to take a lot of substitution, but it's nothing that we haven't seen in the last few slides. Let's see if we can go. And the next two are, well, the next one's the big kahuna of them all. So we have this equation that we came up with in the beginning, and we just came up with this equation. So we're going to take this Vx final here, and we're going to substitute this whole Vx final into the Vx final that we see here. Okay. And this is what it looks like when we write it all out. Again, you have your x initial, you have your 1/2, you have your v initial, and then you have your whole new component for v final, and the time comes down again. So everything was just substituted in. Now we're just going to simplify it, and you can do this any which way you want. Remember that the t multiplies out. So this is vxi times t. And there's two of these, so this is actually 2 vxi times t, right? Because these two just add, this parentheses doesn't multiply anything here. And this becomes at squared, at squared. And everything here is multiplied by 1/2. And so this is then what it looks like. The 1/2 here cancels out 2, yeah. This 1/2 here multiplies out with this at squared, and the x initial stays the same.
That looks familiar.
It does, right? It really does, but it takes a little bit of extra steps with our algebra to get it all in there. And this one, again, notice it's solved for x final. And this one, everyone, put a fat old star next to this equation. This is one of the most commonly used kinematic equations.
Is that what you would get like if you differentiated the position, or if you differentiated the position or something? It looks like v sub 0 plus initial position times the like at, you know, differentiated.
It does look like it. I'm not quite sure I know the other half of what you're talking about, the other equation.
Like if you were to throw a ball up in the air, you know, it looks like that.
Oh, yes, yes, yes. And this is why this is the equation that you want to know. When you take the derivative of this, you're going to eventually see that all of these will go away, and what you'll end up with is just this part of the equation. And in a few weeks from now, a whole new equation is going to come just from this part right here, because we're going to make so many assumptions about throwing a ball up in the air and what is gravity and taking the derivative. Yes, if you didn't recognize it, totally normal, totally okay. But if you just happen to start making these like math connections, yeah, that's it there. And Owen says, yeah, it might be the integral of v final. Yeah, totally right. Integral sounds right. Okay, so again, this one is a very commonly used equation. We're going to use it a lot. And remember, if you have everything here and one of the values just happens to be 0, that's okay. If the acceleration is 0, you cut that whole term out, right? Okay, let's try, I think, the last equation now. Okay, so we have this equation, and what we're going to do now is rewrite this velocity equation, which was one of the, I think the second one we came up with. We're going to rewrite this for t. So we're going to solve this in terms of time, and then we're going to take this value of time and substitute it into the equation that we derived that came to us from the averages. If you don't remember that, this 1/2 divided by 2 and adding these two is your clue that this is the one that came from the averages. And so now we're going to plug in our t into that t there. And what does that do? It's going to eliminate the variable of time, and it'll be the only equation that won't have the variable of time. And that is why we do this. Okay, so we continue with our equation, and now we plug in our new definition of time. And here, I'm going to give you all the time, but you want to multiply it out and convince yourself that you'll get this. And I promise you, you will, right? These two will be a positive. These two will be a negative. They cancel.
Oh, a conjugate.
Yeah, they'll cancel each other out. And then one will be squared. They'll both be squared, right? And then you'll have the negative one. So just practice that at home. But it's algebra. You can do it. And then the 2a carries over. Okay, and so here now we just rearrange a little bit here. We bring in the x initial. What did we do? We bring the x initial over to the x final side. So we combine those, and then we multiply the 2a over, and here's the 2a x final minus x initial, right? Anytime you have x final minus x initial, it's really nice because you can just remember that this is the displacement of x. And then just like we did in the other equations, we solve for like a final component. And so we isolate this variable and bring this one over to the other side. And it becomes positive, which is also nice for us. And this is your last equation of the kinematic equations. This one is used a fair amount, but the big one is the starred one that I showed you on the last slide. And so, ta-da, there it is, the full summary of your kinematic equations for constant acceleration. And this is what this whole chapter is about, and this will carry us for the next 2 chapters or so, until we get to forces.
So this might be a good idea to have on our, like, what did you call it, a formula sheet or something?
Yes, yeah. This is absolutely. Actually, let me just tell you guys too that I will ask you guys to create your own equation sheet, but I will also provide you an equation sheet on the back of the exam. The back of the exam equation sheet will be identical to what you see on the last page of the chapters from the textbook. In fact, all I do is copy and paste. I snip it, right? The formulas from the back of the chapter that we use in our class, I will put them. So you will see them. You will see this, but you know, you have your own way of remembering how to use these, and that's what you'll want to see on the equation sheet. And so the way to use all of these really depends on what's in the problem. We'll have to read about it, right? So for example, if they tell you something is accelerating at 3 meters per second squared, then you know you have an acceleration. If the problem is saying how long does it take for this to happen, you're probably going to have to solve for time and find which one of the variables you can use for time. What if you're not given time at all? If you're not given any time at all and you don't need to solve for time, this might be the equation you go for. The one you use the most in this class is usually this one in the word problems. This is because you can cut so much out here. For example, if they say a car starts out and eventually accelerates to 3 meters per second. What is the initial velocity of a car starting out?
0.
It's 0. And so this V initial goes to 0, right? And they gave you the acceleration. And perhaps they tell you it started and it moved to 5 meters. That means the initial position is 0 and it moved 5 meters. And so that would be 5 meters. And then you could solve, if they give you acceleration, you can solve for time. So it really depends on the problem, and we'll practice that. In fact, I do have 2 practice problems for you guys, but I think we'll start our brain juices tomorrow with that, and we'll just see where we get. And again, we'll adjust as we need for the exam. So yeah, let's try one question, conceptual question before we leave. This is a good one. And I think we can get it. Okay, in the figure, match each of the velocity time graphs on top with the acceleration time graphs on the bottom that best describe the motion. Now remember, each one will give you a different slope. Think about what would be the slope of one of these. So you can write A to D, A to E, A to F, and B to D, B to E, B to F, whichever one you think. Okay, yeah, let's start with A. I like that. Everyone's starting with A.
What does
Okay.
that mean? Match each v velocity time graph on the top with the acceleration time?
Yeah, so the relationship
Like which one's doing both?
Yes, which situation describes both? And the velocity time graph is related to acceleration by the slopes. So you guys are saying A to E. So what do we think about this velocity?
It's linear.
It's constant.
It's
No.
constantly increasing, but it is increasing, which means it is accelerating, and it looks like a straight line. So it is linear, and it's a constant increase. But the word there is constant. Yeah.
A to E.
So perhaps A does go to E. I think a lot of you said A to E. What about for B? What do we think about B?
D.
Hmm?
As in dog.
Yeah, I B as in dog. I see other people. Daniela also says that. Noah too. Owen too. Okay. B to D. So let's see. B has an exponential increase, which means that the increase continues. The increase does not stay constant. The increase continues to go up, to move, right? So I do think these should go together, right?
So it increases increasing.
Yes, yes, yes. I hate to say it that way, and I hate to keep telling you guys over time, but yes, the increase is increasing. The rate of increase is increasing. Yeah. And then let's see the last one. Yeah, it's increasing at an exponential rate. That's right. Okay, and then let's try this one. If this is right, you guys, I think, okay, Saja says C to F, Noah does too, and so does Daniela. Let's see. Oh my God, what did I do? Oh my God. Oh my God. Okay, let's just go to the answers. See if we were right. Yeah. B to D, B to D, A to E, and C to F. So let's look at C, right? Again, we have that similar constant increase. So that constant increase will result in a constant acceleration. And then we have a constant velocity, which will result in no acceleration. And that's why we see that as 0. So yeah, that is good. C to F, since C isn't continuous. Yeah, that's a great way of saying it. Also, process of elimination is correct. All of which should add up. Okay, so we are 2 minutes away. I'd like to just stop here. And I'll let you kind of sit with these equations, practice the homework, and we will try to start with a practice problem tomorrow. That'll probably only take us about 20 minutes, maybe 30 minutes. And then we'll spend an hour on chapter 3, and I'll give us a nice summarized condensed version for what we need to know. And wherever we stop tomorrow is where the exam content, the exam material will also stop. So yeah, and we'll go over that in detail tomorrow. Any questions any questions about lecture today? Oh, Randy, yes.
It's not about lecture today, so I'll wait.
Okay, thank you. I really do appreciate that, just to stay on track. Anything about lecture, we'll go into logistics in a second, but lecture related? Okay. I'm sure that there are at least 25 of you that would like to go. So we're gonna end lecture for today. Please take a look at chapter 2 homework, it's posted. Please take a look at chapter 2 itself, read it, maybe practice. I'm gonna stop recording, and if you have any questions, please feel free to stay, okay?
Thank you, Professor.
Thank you, guys. Okay, and I got a question about how many questions are on the exam. We will talk those details tomorrow, and I promise you it's enough for you to do well. Bye, guys. Let me stop recording. Bye.